Hey y'all, today we're going to be talking about deriving e to the x. Before we get to deriving it, we'll first off talk about what e to the x is, where the number e comes from, and then ultimately we'll land on how to derive the sucker itself. So, without further ado, let's get into it. So before we get into actually deriving the function e to the x, it pays to actually know what e actually is. Now, e, known as Euler's number, is actually just that. It's just a constant. So in our class, whenever you see an e, think about a fancy number kind of along the same order as pi. Now e can be defined in multiple ways. One way we can define e is the limit, as n approaches infinity, of the function 1 plus 1 over n to the n power. There are actually other ways to define it, such as adding sums or adding together all of the fractions of 1 over n factorial. However, this is probably the one that you'll remember as it relates to compounded interest. Now, as far as we're concerned as well, e is going to be approximately 2.71828. You know, that's not really necessarily important to know what it approximately is, as there's a button on your calculator for it. However, I think it makes it less mysterious. As I just mentioned, maybe its most famous application as far as business goes would be continuously compounded interest. If you look at this formula right here, 1 plus 1 over n to the n power, that looks an awful lot like the compounded interest formula. By letting n go to infinity, that's the same idea as letting time go to continuous from discrete. So that's all that e is, not anything too mysterious, it is just a fancy constant. Now let's take a brief excursion into an application of e that is commonly used in the world of business. And that is going to be that of compounding interest. So, first and foremost, let P be the amount deposited, T the number of years, A the account balance, and R the annual interest rate. Now, if interest is compounded n times per year, then we have the following relationship. A, the account balance, is equal to P times the quantity 1 plus R over n, all to the n times t power. So this would be where you're compounding perhaps yearly, monthly, daily, or even secondly, right? Where there are gaps of time between when you're compounding. However, notice how similar that thing is to the definition of e. Therefore, if we let time go to infinitely small, meaning continuously, if you compound your interest continuously, then A is equal to P times e to the RT. So this becomes e right in there. And this is affectionately known as PERT. Now let's go ahead and see an example of how these two formulas could be played out. Now let's go ahead and try an example of this compounded interest formula. So let's consider the following situation. $15,000 is deposited into an account that pays 8% interest compounded quarterly. How much money will be in the account in 30 years? And then similarly, what if this was compounded continuously? Let's start with the first question. As we're compounding quarterly, that means I need to use my compounded interest formula, which was A is equal to P times 1 plus R over n to the nt, where n is the amount of times you're compounding per year, R is the interest rate, t is the amount of years, and p is the principal, or the amount deposited. Well, once you have the formula, it's really just as simple as plugging in where you see fit. So for instance, our principal, or the amount we're depositing, is $15,000. Continuing to fill in, we see that our interest rate is 8%, which we write as 0.08. Divide that by the number of times we're compounding per year, 4 since we're compounding quarterly. And then last but not least, we're doing it for 30 years. So our power is 4 times 30, or 120. If we go ahead and simplify that out, what we should end up with is 161,000. Sorry, I got my answer right behind you actually. $477 and roughly 45 cents. So that money definitely grew. Now if we want to compound continuously, we use a different formula, PERT. exact setup, once we have the formula, we just go ahead and plug in appropriately. So, P is still $15,000. And then we have E. R is still 0.08. And T is still 30. Now, upon calculating that out, what we get for an answer is $165,000, 347, and roughly 65 cents. And that will be our answer. Now, given the exact same interest rate, the exact same time, it actually makes sense that when we compound continuously, we will be getting more money as we're building interest off of more money more quickly. So therefore, that is a common check that you should do when you are doing these types of problems. Now let's get into the calculus of E. Now let's start talking about how to derive a function e to the x. This is actually one of the nicest rules in calc. Given f of x equals e to the x, where it's just x in the power, then f prime of x is actually just equal to e to the x. It just stays the same. Now this is a consequence of actually another definition of e to the x, which you could justify by going into calculus 2. However, we're business cal, so we're going to keep it at that. E to the x just stays the same upon deriving. Now a little bit more generally, and probably a better rule to have memorized, is by the chain rule actually. If you have f of x equals e to some power involving x, which I will signify another function g of x up top, then the derivative f prime of x is the derivative of the power g prime of x times the original thing. The reason this comes from chain rule is you can think about having a function, g of x, trapped by another function, e to the blank. Therefore, the derivative of the outside is just e to the g of x. Now I have to times it by the derivative of the inside, the power, g prime of x. This actually will help you memorize this rule, and this works on a broader context. A quick for instance of this rule would be the following function. Quick example, if I have the function y is equal to e to the x squared plus 2x, when I derive this, y prime, since I don't just have an x up here, I actually have to use this more general rule, which is justified by the chain rule. Deriving this function will be the derivative of the power, 2x plus 2, times the original thing, e to the x squared plus 2x. And you can actually prove that this rule follows from, or this rule gives us this rule, because the derivative of x is just 1, which gives you the original thing back. So let's get into a little bit more examples on how to derive more complicated things. Let's go ahead and start on some examples. The first example will be y is equal to 3 times e to the x. The reason we want to consider this example is because constants will actually behave the exact same way as if I had the function 3 times x squared. They'll actually just be copied down. So therefore, when I derive y equals 3 times e to the x, the constant stays, so I just copy that, and then I derive e to the x. But wait, the derivative of e to the x is just itself, giving me y prime equals 3 times e to the x. As a second example, let's consider f of x equals e to the x squared plus 7. This is where it's going to be more helpful to consider a more general rule. When you have a more complicated power, remember to derive e to some power, you take the derivative of the power and multiply it by the original function. The derivative of the power, in this case, is just 2x. Now to complete the problem, I just multiply it by the original function, e to the x squared plus 7. You can drop the parentheses in this case because we're just multiplying everything and it's not a problem. Lastly, let's consider the function g of x equals 7 times e to the negative 1 over x squared. In this case, we have a negative 1 over x squared. It's helpful to rewrite that as always. So my first step without deriving will be to write this as 7 times e to the, well, the way to make this thing not a fraction is by making this power negative. So we have negative x to the negative 2 as our power. Now we can actually take the derivative. So remember, when I derive it, first and foremost, constants get copied down. This is the exact same as any derivative rule that we've done. 7. Now I go into deriving this e portion. When the power is more complicated than just x, I take the derivative of the power, which in this case is 2x to the negative third power. Then we multiply it by the original function. E to the negative x squared, or x to the negative 2. Simplifying out, what we can go ahead and land on is 14 x to the negative 3 e to the negative x to the negative 2. You could get rid of those powers. However, I won't require it. That would be plenty simplified, so long as you go ahead and combine the constants through multiplication. Now let's get to some even crazier examples. Just as in previous sections, when we added a rule, it did not mean that we could forget the rules prior. In light of that, here are 3 more examples. First function, y is equal to e to the x plus 1 divided by e to the x minus 1. Yet again, if you could do algebra on this, that will usually pay off in the long run. However, in this case, we cannot. Yet again, as in previous sections, we must ask, what is the big picture rule right here? Well, I have something divided by something, so the big picture rule will be a quotient rule. Meaning my derivative will follow the quotient rule pattern. Low, e to the x minus 1 times d high. The derivative of e to the x is just itself. And then the derivative of 1 becomes 0, so d high ends up being e to the x. Low d high minus high, e to the x plus 1, times d low. The derivative of the bottom one of e to the x is just e to the x, and then the negative 1 goes away upon deriving. All over the square of what's below, meaning e to the x minus 1 squared. Now usually with product or with a quotient rule like this, you actually get a lot of simplification. And to go ahead and see this, if we carry this out real quick, distributing in, we'll get 2, or e to the x times e to the x, giving me e to the 2x up top, e to the x squared, minus e to the x. Distributing in right here, we'll get minus e to the 2x, minus e to the x, all over this thing squared. And you'll notice right away that these guys cancel, leaving me with negative 2 e to the x on top over e to the x minus 1 squared. As a quick justification, just because I want to go ahead and go into it, if I have e to the x times e to the x, this thing right here, what we're going to go ahead and do is add the powers, since we have that going on. You could think about it e to the x squared, but power to a power, you multiply it, giving me that e to the 2x. So that's where we get that from. Now let's go into the other problems, if I'm leaving myself enough room. F of x is equal to x times e to the negative x. Yet again, think big picture rule. Something times something means product rule. So when I derive, if I can write it right here, I follow the product rule pattern. First d second plus second d first. First is x times d second. This might be the trickiest derivative you'll encounter the entire year. Not so much that it's a tricky one to do, however it's very tempting to do it wrong. The reason is, our power is not just x. So we have a negative there. So remember the more general rule. When deriving e to the blank power involving x, you take the derivative of the power, negative 1, and multiply it by the original function, e to the negative x. So we don't just get e to the negative x here. We get negative e to the negative x. First d second. Plus second e to the negative x times d first. 1. I apologize about writing downwards. If we go ahead and simplify that out, what we would get is negative x e to the negative x plus e to the negative x, which you could write, if you want, as negative, or if you factor out the e to the negative x, e to the negative x times either 1 minus x or negative x plus 1. And that would be a perfectly valid answer. Last but not least, let's consider the function g of x. This one can be tricky because notice that there's something different about this e than there is about any of these two e's. This one does not have a power. So remember, e is just a constant if it does not have an x in the power. So 3 times e is just a glorified constant, kind of like 2 times pi. So therefore, when I derive it, I just get 0. And that's due to this thing being a constant. A glorified one at that. To finish up, let's go ahead and talk about an implicit differentiation example. Here we have 2 more examples to round out our exploration of the functions e to the x. First and foremost, find dy over dx implicitly given the following equation. X squared times y minus e to the y minus x times y equals 0. A little bit of a contrived one. In this case, implicit differentiation works the exact same way. We're just adding on more rules. So therefore, derive everything. X squared times y and negative x times y are both product rules, so we got to be careful on them. When I derive x squared times y, since that is a product rule, we have first x squared times d second. The derivative of y is just 1, but remember to directly attach a dy over dx. First d second plus second y times d first 2x. That's the derivative of this guy. Now we move on to negative e to the y. Now remember, when you're deriving e to the blank power, all it is the derivative of the power times the original function. The derivative of the power ends up being dy dx. The minus gets copied down because it's a constant. The derivative of the power is dy dx, and multiply it by the original thing, e to the y. That's the derivative of this guy right here. If you want to flip the order, go for it. Last but not least in deriving, this negative x times y is yet again another product rule. So we have first negative x times d second dy over dx plus second y times d first, negative 1. And that's all equal to 0. If you want to go ahead and do this and then distribute in the negative, you can do that. It'll give you the same answer. From here, simplify out your work, make it prettier. X squared dy over dx plus 2xy minus e to the y dy over dx minus x dy over dx minus y equals 0. All I did was kind of order it neatly. Then what we're going to go ahead and do is do that dy over dx rodeo. Round up all the dy over dx to one side, push everything else to the other side. Now most everything's going to stay on this side, leaving me with x squared dy over dx minus e to the y dy over dx minus x dy over dx. That's all equal to adding over the y and subtracting over the 2xy. Y minus 2xy. Penultimately, go ahead and factor out that dy over dx, leaving me with x squared minus e to the y minus x equals y minus 2xy. And then lastly, divide through by an answer. dy to get your answer. dy over dx equals y minus 2xy divided by what was left over, x squared minus e to the y minus x. And that ultimately gives me my answer. So yet again, implicit stays the same. We just pick up another rule, how to derive that e to the blank power. Now let's go over to another classic problem. Find an equation for the tangent line to the graph of the function f of x equals e to the 3x minus x squared at the point 3, 1. Yet again, when we're finding equations of tangent lines, the first thing we want is the slope. In order to get the slope, that screams find the derivative. So first step, get our hands on f prime. Now the derivative of e to some power involving x is the derivative of the power times the original function. The derivative of the power is 3 minus 2x. The original function is just e to the 3x minus x squared. That's our derivative. To get the slope of the tangent line, because remember we're after something of the form y equals mx plus b, we go ahead and plug in our point to the derivative. So m better equal f prime of 3. Plug in x to the derivative. Well, this will just be 3 minus 2 times 3 all times e to the 9 minus 9, or e to the 0th power. Now that's just 3 minus 6, or negative 3, times 1, or times e to the 0. So my slope is negative 3. From here, what we go ahead and do is use point-slope form. So last but not least, we have y minus y1 equals m times x minus x1. So y1 in this case, using our point, is 1 is equal to m negative 3 times x minus x1. x1 is positive 3. If you don't mind me writing up top because I'm kind of running out of room, what this could give me as an answer, upon simplifying it out, I distribute in the negative 3, I get y minus 1 is equal to negative 3x plus 9, and then ultimately adding over the 1, you should get y is equal to negative 3x plus 10. And that will be your answer for the equation of the tangent line. Yet again, you could graph that on Desmos or your favorite graphing calculator, and that will give you a good check as to whether that really is a tangent line to this graph at this point. Hey y'all, thanks for tuning in today as we explored the function e to the x and its derivatives. As a quick recap, e is just a fancy constant. It does come up in compounded interest quite a bit, so that's why it's relevant to you, so it is worthwhile being able to work with, but just think about it as a number. As far as the calculus is concerned, if f of x is equal to e to some power of x, e to the g of x, that's how I word it, then f prime of x is the derivative of the power times the original function, g prime of x times e to the g of x. That's going to be your rule for the section. This is the one to have down for the final. If you have that one down, the only other thing to remember is to respect the previous rules. So if you have a quotient rule, you got to make sure you still know how to do the quotient rule. Product rule, know how to do product rule, and then ultimately remember that this actually comes from chain rule. So with that being said, feel free to attempt all the homework, ask me any questions that you have, and good luck.